From Chicago, welcome to 3Degrees Discussions. I'm your host, Mike Vasquez. This is a podcast devoted to the stories behind the innovators, entrepreneurs, and leaders in the 3D printing industry.
The conventional way is to reference something out of MMPDS, which is the handbook of all, source data from a publicly available specification. And so if you look in MMPDS, there's a methodology for how you determine these values, these minimum design values. And it's statistical methods. It's a T90 or T99 value. The problem is that when you look at how the definitions are assigned, what's a heat, what's a lot, how many samples do you have to take, orientation dependencies. None of that was spelled out then, and I don't even think it's spelled out now.
That was Craig Brice. Craig is a professor of practice in mechanical engineering at Colorado School of Mines. He is currently the director of the Advanced Manufacturing program, which focuses on undergraduate and graduate education in additive manufacturing and other advanced manufacturing techniques. He is also involved in additive manufacturing research with the Alliance for the Development of Additive Processing Technologies, or the ADAPT Center, and serves as the director of the ADAPT consortium. Dr. Brice has been working in additive manufacturing for over 20 years, beginning with the first commercially available AM system sold by Optomec in 1998. He has spent his entire professional career working in additive manufacturing, with time spent at Lockheed Martin Aeronautics Advanced Development Programs, Skunk Works, Lockheed Martin Space Advanced Technology Center, and NASA Langley Research. Before he gets started, head over to www.3degreescompany.com and subscribe to the podcast. Remember, you can listen to the show anywhere you download your podcast, including Spotify, Apple, Amazon, or Stitcher. All right, Craig, thank you so much for joining the show today. I'm excited for the conversation. Let's start where I do with all my guests, or most recently, at least. Tell me about life early on. Where were you from? Where you grew up? What got you down the path of maybe engineering in those early days?
Okay, sure. So I grew up in the Midwest. Was born in Iowa, moved around a couple of times in Iowa before I moved to Missouri, southwest part of the state, around 11 years old. So I kind of claim that as my home, because that was where my formative years took place. In terms of my interest in science and in engineering, it's hard to pin down when that took place. I was always good at math and science. I didn't really know where that was going to lead me. Because I lived in Missouri, I applied to what was then the University of Missouri at Rolla, which is now the Missouri University of Science and Technology. Again, thinking I wanted to be an engineer, but not really knowing what type of engineer. In fact, I like to tell people that my freshman year, I was undecided, and probably every 2 weeks, I was a different type of engineer. We had a course that we, as freshmen, went to, and we hopped around departments and saw what they did and got to talk to faculty and other students. And so I was changing my mind on a weekly basis. And the interesting, shift in my mindset was one of those department visits. We toured the metallurgical engineering department, and they had all these little samples of metal laid out on the table. And you had a little survey that you had to do. Just by picking them up and visually looking at them and feeling them, you were supposed to guess which one they were. And there were density differences and luster differences. And I won. I got them all. I don't know if I got them all right, but I beat everybody else in my tour group. And so I got a little special gift or something. And I'm not sure if that's what keyed me into taking the path of metallurgical engineering, but that's a story I like to tell. So that was how I ended up at least getting my start in metals. Now, when I, through kind of serendipity, I suppose, I was intending to go to grad school right after my bachelor's degree. And I applied to 3 schools. And I visited two of the three schools that I'd applied to and kind of struck out. I didn't really connect. I didn't connect with any particular faculty member. And so I went back to Missouri Rolla, and I kind of, I guess, complained to one of my professors there, who was kind of my unofficial advisor. And his advisor in grad school was at Ohio State. And he reached out to him and suggested I get in touch and contact him. And that was Professor Hamish Fraser. So hadn't even really applied, wasn't on my radar. I thought I'd give it a shot. Hamish invited me out. I guess I fell in love with it. And again, through kind of a serendipitous connection, when I showed up to start my master's degree was just about the same time the very first serial number 001 Optomec lens machine got delivered to Ohio State to sit in Hamish's lab. So I was lucky enough to be hands-on and working with the first commercially available metal 3D printer that was out there. And so that was where my career in additive started, and I haven't looked back.
So did you like working with your hands? Was that always something that you wanted to do as part of your kind of engineering pursuits?
It's funny because I now have a teenager who's considering engineering as a career, and I look and I think, well, he's not really hands-on. He's not a tinker. We have this assumption that as an engineer, you should be taking apart your radio and putting things back together. And I was never really that way either. And I did like the hands-on component to it of working with this first 3D printer at Ohio State. On the other hand, there were a lot of frustrations, right? It was a brand new machine. The documentation wasn't 100%. Things broke all the time. I didn't know anything about lasers. I didn't know anything in hindsight about safety in terms of metal powders and all of these things that I look back on and think, holy cow, it's amazing I didn't, fry my eyes or do something like burn down the building. So I did enjoy that hands-on component, even though oftentimes it was frustrating.
So was that a master's, or was that also kind of where you kind of got into PhD as well?
Well, I went in kind of undecided. I wasn't really sure how long I wanted to stay. And the deciding factor was my project was funded through a grant from Lockheed Martin. So Lockheed Martin had provided a grant to fund a student, to Hamish Fraser. He put me on that project. As part of that project, I did an academic year in Columbus, and then I went to Fort Worth, Texas, to the Lockheed Martin facility there, where they had just spun up probably one of the first large industrial R&D labs in metal 3D printing that I know of. And I was kind of blown away by it. It was phenomenal. The people, the excitement behind it. We were, first to the party on the lunatic fringe. It was an exciting time. And so I went back to school, and of course I was going to finish up. And it was kind of at that point that I decided I can't delay this. I can't delay getting out there and getting into industry and doing some work. So I chose to leave with a master's degree. I eventually did get a PhD while I was working, but I couldn't pass up the opportunity to not jump on that new opportunity at Lockheed Martin.
And so what is it like to work in one of Lockheed's a big company, right? A lot of different focus areas, a lot of different groups, and a lot of different kind of industrial focuses. So was this lab specifically focused on developing 3D printing as a technology or qualifying materials so that it could kind of branch out, or kind of what was your first kind of role, or kind of within that group there to achieve kind of 3D printing to what end within in the organization?
Right. So interestingly enough, the president of that particular business unit was a champion. And so we had kind of high level cover to do interesting things, right? It was at the highest levels. The president of that business unit had seen, so we had some stereolithography equipment that was used to make wind tunnel models or just shapes, demonstration articles. And he had seen that. And what he had told the guy who hired me in, Brian Rosenberger, he had told him, I want you to go pour me an airplane, because he was thinking, stereolithography, big vat of goo, and you lift an object out of it. And so, it's way more complicated with metals, but we always kind of hung on to that tagline, pour an airplane. That was the concept. So early on, it was quite unusual, because while most people who were just getting into additive were thinking, what parts can I replace? I want to do a one-to-one part replacement, make this out of that, and not really change anything. Just do it by a different method. Our guidance was, don't bother with that. We're going to jump right over that, and I want you to make an entire airplane. And of course, that's fanciful, and it was even today fanciful and well beyond what additive is capable of. But it was nice to have that longer term vision, not be bogged down by, make this little widget and incrementally get there. So we could kind of swing for the fence. And I was the metallurgist on the team. We had the guy who started the project. He had a background in conceptual design and airplanes. We had a chemical engineer, we had an electrical engineer, we had a hands-on technician, we had a computer software guy. So it was a really cool group to work in. And we were all kind of tackling individual problems. And I mean, there were plenty of problems to work, and there still are plenty of problems to work. So it was an exciting time for sure.
And so how did your role can you speak about kind of that, the evolution of that project, or kind of your career within Lockheed, and kind of where that, we know where it started, kind of where did that lead in terms of different technologies? Did you say you started with kind of Optomec type systems as well, and then kind of continued to explore that path?
Yeah. So the system that they had installed there was blown powder, DED, directed energy deposition, on the scale of that kind of Optomec, 1 millimeter resolution capability. But that system was on the end of a 6-axis robot arm inside of a giant tank, so that we could do complex shape, off-axis path planning. So instead of 2-dimensional stack slices, we could slice in any orientation. That was a really cool thing we were doing even back then. It didn't take long for us to realize that making parts at that length scale, there wasn't many airplane parts that were going to be valuable at that length scale. So we started looking at other techniques, and we branched out. We were the first to look at electron beam DED. We went and knocked on Siaki's door in Chicago and got them interested in doing some large scale DED for us. And they're still doing it. They're selling machines today. So we recognized early on we needed higher deposition rates. We needed to really throw a lot of material down, knowing that we were going to sacrifice resolution, but we could come back and machine it. So you have to find kind of the sweet spot of the cost to add plus the cost to subtract, and where do those curves intersect. Eventually that led to, what we were an R&D lab, but eventually we had to show we were impacting a platform, and that platform happened to be F-35. F-35 is one of the few, if not only, defense platforms that has a built-in kind of affordability metric to it. So you couldn't just, it couldn't just be cost what it cost. It had to be performance, but consider cost as a factor. And so our project was an affordability initiative to swap out titanium die forgings with electron beam DED parts. And these are big parts, as big as a table. And that was a very eye-opening experience for me, because I was an R&D guy, and now I was in the world of process specifications and qualification, and learning about how something goes from the lab and makes it onto a platform, which is, now is kind of what I like to focus on in my work in my current job, because it's a huge burden and it's a huge hurdle. And if we're not working to clear that hurdle, it's gonna really be limiting. Anyway, kind of to wrap up that story, we went through an entire qualification program that was funded by F-35 and overseen by people from the program office at the Air Force, and collected a tremendous amount of data, sorted through all the variability, both in terms of the material, the wire that we source, and the samples that we made. Turn the statistical crank, if you will, and got a number out that we used to design against. And that number was close enough. It was close enough to what that part needed. An interesting thing I've learned along the way is that, an individual part has many criteria that it's designed against. And in terms of a titanium airplane part, it's oftentimes durability and damage tolerance, which 3D printed titanium has. That's where it shines. So we were in pretty good shape property wise. What we failed to really forecast was the challenges in inspection. You can't fly a part if you can't either have confidence that it has no flaws, or inspect it such that you can find those critical flaws that are going to cause problems. And parts that big, we weren't mature enough in our inspectability methods. We still don't quite understand the effect of defects. Even if we could see a flaw, do we know what it's going to do and how it will perform? And I guess finally, the deal breaker was, for those that understand or have been around 3D printed material, and if you know anything about metallurgy, the grain structure is really unusual and unique, and it's oriented, and it's columnar, and it's got these weird features, and that tends to have problems when it comes to traditional inspection methods. Things get noisy really fast, and you can't see as deep as you could through a normal conventional product form. And so, the lesson learned was this secondary operation, which we weren't even thinking was going to be a problem, actually was the problem. The data, the performance, the properties, the ability to make the parts and make them economically feasible, all of that shook out pretty well. It was inspectability that tripped us up. So big lesson learned there.
And so at this time, since you were so early on, were you kind of working in tandem with the regulators or kind of the qualification body to kind of come up with some of these standards? It was so new, right? Like it hadn't been done in many respects before. So how did that dynamic work?
Yeah, that's a great question. And it was at one point, you run up against this wall and you say, well, the conventional way is to reference something out of MMPDS, which is the handbook of all, sourced data from a publicly available specification. And so if you look in MMPDS, there's a methodology for how you determine these values, these minimum design values. And it's statistical methods. It's a T90 or T99 value. The problem is that when you look at how the definitions are assigned, what's a heat, what's a lot, how many samples do you have to take, orientation dependencies, none of that was spelled out then, and I don't even think it's spelled out now. I think MMPDS and other standards bodies have recognized we have to write this down, and so they're in the process of writing this down. Back then, I kind of just threw a dart at the wall and started saying, well, this will constitute a lot, right? A lot is if I make 5 parts on the same base plate, but then I cut each one of them off and heat treat them separately, are they still the same lot? And, we didn't know. Nobody really knew. So we kind of just made our own decision. And we got it blessed by the internal materials and process people at Lockheed Martin. We got it blessed by the materials and process people in the F-35 program office. And so we were all on the same page. We all agreed to the terminology. We all agreed how we were going to approach this, even though nobody had really formally documented this. And we went off and pressed on. So we did engage, in the aviation side. The regulatory bodies flow that down, right? We can't force things up. It's flowed down from on top. Interestingly, one of my biggest projects right now is working with ground vehicles in the Department of Defense. And in that case, there is way less top-down push from a regulatory agency because the criticality is less, right? Part breaks, you tow something back to the shop, as opposed to a $130 million airplane. When something breaks, that's a really bad day. So yeah, you kind of have to, depending on what market you're in, aviation and bio being the most stringent, you're going to get flow down from those regulatory bodies, and you're going to have to work with them. And we're all still figuring that out right now as we go.
So what was the timing for that entire project, kind of from when it kind of kicked off to, hey, we've got something qualified, signed off, ready to kind of put on an airplane?
Yeah, it's the qualification part was, I left right towards the end of it to take a job at NASA. And it was probably close to 3 years, start to finish, to do that. And, I won't share the cost of it because I probably shouldn't, but you can imagine, right? And so when you look at the time and the cost to do qualification on one part or one part family for one vehicle, that's where I became kind of a zealot, if you will, for doing qualification better or taking a different approach, because F-35 can afford that time and cost, but most other programs cannot. So.
For sure. And so kind of after Lockheed, it sounds like NASA was the next step. You want to continue the career trajectory? Yeah.
So it was time for a change after about almost 11 years at Lockheed Martin. And I had a fun opportunity to go out to the East Coast and work for NASA. Really didn't interrupt things that I was doing. They had a Siaki machine at that facility. I was already kind of an expert in that particular brand of additive, having been working on it for, by then, a decade, and going through a qualification program in F-35. So at NASA, I had a little bit more, I kind of stepped back into the more research and development role, as opposed to when I left Lockheed Aeronautics, I was, less R&D and more implementation. I was at that kind of maturity level where I'm ready to hand it off to the materials and process people, and then they push it on to the platform. At NASA, I got to take a step back and go back kind of to my original passion, which is the material behaviors, alloy development, fun things that you can do with additive that you can't with other techniques. We, our Siaki machine that we had there had 2 independent wire feeders. So I built a stacked nozzle where we could feed multiple wires, did some graded alloy work with that. My career has kind of always been, skewed a little bit towards the large scale DED side of things, but I was also working in other techniques as well. Powder bed, arc based. We did some arc based way back in the early days at Lockheed Martin. I continued some of that at NASA as well. So yeah, it was a fun shift into a different area, still in aerospace. We tried to push parts into the last shuttle mission, was going up to retrieve, on the way back, they were going to retrieve a broken ammonia pump off of the International Space Station. And they had this big, it looked like a big socket wrench, but it was like 3 feet long. And they needed this to extract this ammonia pump and stow it into the space shuttle cargo bay. And we did a lot of work to try and get that, the little socket end that we were going to E-beam DED fabricate out of aluminum. We tested it, and we proof tested it, and we broke it, and we examined it and thought we had a chance to get something flown. And that was when I learned, the difference between manned space flight and unmanned space flight. And it's the regulation and the safety aspects are at least an order of magnitude, if not higher. And so unproven technology, even though it was a low hanging fruit and low burden, it never got to fly. But we were making progress and keep pushing on the technology. And now we've got parts on Mars. We've got parts orbiting Jupiter. I say we, collective we, the industry working in additive. So it's getting out there. It's fun.
And I suppose NASA too has a little bit different mission than a Lockheed or the F-35 program, where a lot of the work that you do is for the shuttle or for one of the vehicles or a program. But part of that work, I imagine, can be shared more publicly in terms of helping the industry as a whole move, whether it's increased qualification time or decreased qualification time or insight on new materials or methods as well.
Yeah, it was certainly working inside of a big corporate entity. You run into sharing and openness issues. Working for the government, it was, well, you're required when you receive funding from the government through a lab like that to publish your work and be open about what you're doing. So it was a nice change, and it was, it felt like I was having more of a contribution than just outside, as opposed to just that one company. And in fact, I had one of my frustrations kind of when I was at Lockheed viewing the government agency landscape was that there wasn't enough talking and sharing amongst the government players. And so while I was there, I created we called it the government only working group on additive manufacturing. And so the only people invited to the table were civil servants or, representatives, contractors of government federal facilities. And so it gave us the opportunity to try and, share and collaborate and know what this agency was funding and what this agency was funding. And if there were ways we could collaborate. And I know that, I was at NASA for 5 years, and once I left, I think it kind of dissolved. I don't know whatever happened to that organization, but I do know now that there's so much going on in the additive world. It's hard to keep up. And so I know the institutes like America Makes have helped fill that void. So they're bringing everybody to the table and making sure that people are knowledgeable about what's going on and what people need.
Certainly. And so it was after kind of spending the time at NASA that you transitioned into academia, or was there another step in between that?
There was another step in between there. So one of my buddies, Slade Gardner, he and I worked at Lockheed Aero in Texas, and went our separate ways when I went to NASA. And then he was at Lockheed Space in Colorado. And so he had just secured a very large program internally funded by Lockheed to do additive in the spacecraft side of the house. And so he was desperately looking for people to help. I was not necessarily looking to make a move, but I couldn't pass up the opportunity. And while I'd never really spent any time in Colorado, it was also kind of a bit of a pull. So I picked up the family and we came to Colorado. and so, yeah, we worked for a little while on that project, as tends to happen with big corporate entities like Lockheed. Things change quickly, and without rhyme or reason sometimes. Shortly after I came, some of the funding got shuffled around. Slade ended up starting his own company, Big Metal Additive. He's still here locally in the Colorado region. I stuck it out for another close to a year and a half, 2 years. But by then I was collaborating quite closely with the folks here at the School of Mines. So where I worked at Lockheed and where the School of Mines is about 20 minutes away. And so as an R&D person inside of a big corporation, we always look for opportunities to collaborate with academics. And in particular, the academics here at Mines were really good to work with. Aaron Stebner, who was here at Mines and is now at Georgia Tech, he was my main connection, and we formulated kind of this research center, ADAPT, Alliance for the Development of Additive Processing Technologies, which is the research center and industry consortium here at Mines. Getting involved in that while I was at Lockheed kind of got me interested. Then Mines asked me to step in and teach an intro to additive course for a faculty member who was off doing some other things. And so I taught as an adjunct in the evening while I was still full-time at Lockheed Martin. It had never crossed my mind to be a teacher or to be in academia, but I kind of liked it. I enjoyed, engaging with students. The students here are top of the pile. They are all very, very sharp, and it's very exciting to be around them and their creativity and, be part of transitioning that knowledge base onto the next generation. So as things kind of got less and less favorable at Lockheed and I started getting stronger and stronger connections here at Mines, I thought it was kind of an obvious leap. It didn't require me to move my family again. And it got me the opportunity to do the teaching side, but also get into the research side where I'm not purely in aerospace, which had been my career up until that point. So now, as I mentioned earlier, we're working problems on ground vehicles, trucks for the Army. And I can have conversations and go after funding in bio, in other commercial products. So it's fun to get outside of that aerospace. Aerospace will always be my go-to in terms of my expertise and my knowledge. But it's fun to work other areas of additive because it's getting pretty exciting elsewhere.
And also, you probably have a extensive network from all your time in both at NASA and at Lockheed, and with all the commercial companies that you worked for. On the flip side, now kind of as an academic, like you can kind of leverage some of those connections to do bigger projects as well.
Yeah, absolutely. In fact, one of the key things I tell my students is your network will define your career path. Rarely do you apply to an online posting and get a job. You know people, you know what they're doing, they know you, and when they need you or when people need employees, that's how you find connections. That's how you find projects that you can work on together. So yeah, it's through my various jobs. I've gotten to know a lot of people in a lot of different places, and it's led to a lot of fruitful collaborations and just fun engagement. So that's good.
And so nowadays, like as you from the professor side, what are you seeing in terms of trends from students kind of you interact with as it relates to additive? Are people kind of pursuing metallurgy, like knowing that they want to go into additive or work in space or aerospace? Like what's the general pattern that you're seeing now with I would say a little bit higher visibility of additive manufacturing, 3D printing than it was certainly 5-10 years ago?
Yeah, I would say the most visible change, and I guess the first time I taught as an adjunct was 5 years ago. And I always start my first class with, how many of you have had experience? Either I've got a 3D printer at home, or my roommate has one, or I've used one at my internship. And the first time I taught, maybe one or two people raised their hands. And now when I ask that question, the majority of the room raised their hands. Everybody has interacted with it, whether it's, now it's not just the labs that I or my colleagues that are kind of dedicated to additive have, but like every professor has one in their lab just for making, little brackets or something for an experiment. So everybody has gotten exposure to it, and it's kind of changed. It's changed things a lot. So it speeds up that learning curve to get people comfortable. The flip side to that is that I feel like I spend a lot of time unteaching what students have taught themselves or think that they know based on the perception and the broader media, right? So no, it's not going to change. It's not going to do away with every other form of fabrication. No, not everything is going to be 3D printed in the future. It's another tool in the toolbox. It's got advantages and disadvantages. Know when to use one versus the other. So I feel like I'm less having to teach them about what it can do and teach them more about what it can't do. Don't forget, there's other methods out there. If you have to make 100,000 of something, injection molding is probably better than your extrusion printer. So the perception has changed as it's become more popular and people are paying more attention to it.
And is it a combination of both undergraduate and graduate programs, opportunities, kind of research for at Mines as it relates to additive?
Yeah, the program that I run is specifically a graduate non-thesis program plus a certificate. And we're pushing both of those online. The non-thesis master's degree will be fully online in the fall of 2022. But we do engage with undergrads as well, even though it's not formally part of a degree program. I'm sponsoring a senior design team this semester that's building a chocolate 3D printer, which is pretty exciting. I've been promised that the review this week, there will be samples, there will be chocolate to be eaten. So I'm very excited about that.
Just in time for Valentine's Day, right?
That's right. That's right. I have another undergraduate student who we have kind of special programs where students can apply and then get kind of paired up with a professor and then, given some funding and some resources to go do some laboratory work. And so I'm working with a student now to do some proof of concept. He's a freshman and he's phenomenal, and do some demonstration work in cold spray. And so I enjoy the opportunities to work with the younger crew because, the earlier they can get excited, the more fantastic their ideas will be when they get to me in graduate school. We just wrapped up a competition. We did a competition it was supposed to be last semester. We delayed the final judging into January because of COVID. But one of the teams, we had 3 teams competing, and they were all tasked with designing a wrist-mounted scoop for astronauts to use, so that when they're walking around and they want to sample the soil, they can just put their little scoop down and sample it. We didn't tell them to use 3D printing, but of course everybody gravitates towards that because they have to make a demonstration prototype. And one of the groups was a group of freshmen, and they did phenomenal. And so it's going to be exciting to see how they progress over the course of their career here at Mines. But the way students are approaching and using additive at the early stages of their academic career is impressive. So it bodes well for our future, I think.
And do you see the industry pull as well? Like, are students getting hired into jobs related to additive?
They are. There's my perception is that there's way more need out there than there is people to fill them. I think that's more true at the higher level of experience, but certainly entry level students. I do try to set a reasonable expectation that you're not going to necessarily go out and work exclusively with additive. You may be working in an area where you incorporate that into your design or your process flows. But, I think the very first graduate out of our master's program, she went straight to Blue Origin working 3D printed rocket engines. So we've got people, big and small companies. We've sent 2 students over to Slade at Big Metal Additive. And it's fun to see them go straight into an additive centric job and just excel at it. So that's fun. Yeah.
Awesome. Just 2 questions left for you. So the first one is kind of as you reflect on kind of the conversation today and kind of your career in general, kind of what's exciting you kind of in the next kind of 6 months to a year, what's on your radar in terms of kind of things that you're excited about, either industry related, kind of personal kind of research and work that you're doing?
Yeah. So one of the big benefits of academia is that with appropriate notice and blessing, I can do some things on the side. And I'm, encouraged to do that as a faculty member because, the students get to see that. And so demonstrating that we can not just be instructors, but that we can apply what we've learned and what we're doing externally is encouraged. And so I've got, I started a couple of different companies, one by myself, making consumer products. I call it Tessellation Studio, which those in the business recognize. Those outside the business, I have to explain it to them. I also secured the domain builtwithtriangles.com because I think people can remember that. People can't always spell tessellation, including myself, but builtwithtriangles.com. So that's where I'll send people. But my first product is a slim wallet that's 3D printed out of titanium. It was really an interesting project because part of it was educational for me as an instructor because I've worked a lot and I've bought services from companies, but never with the mindset of that I'm going to resell this and try to make money with it, right? And so one of the things that I have to unteach my students, as I said, is the cost factor. I mean, it's oftentimes way more expensive, and I got to learn that firsthand by trying to make this slim wallet that's got a titanium front to it. But I did find a company that could produce it where I could make money. And so I'm in the process of having all the bits and pieces made. I'm not doing any of the work myself. I'll just do final assembly and package and sell them. And those, my online store should be open next month. So that's kind of my exciting thing that's happening. One of my exciting things that's happening on the side. And the other one is a company I formed with a partner, looking more at the mobile fabrication aspects. And this isn't exclusive to 3D printing. This spans all sorts of fabrication methodologies. But we're working with a customer that our first customer has needs in a remote area and heavy equipment that's breaking all the time. And so additive is a nice solution as opposed to spares in a warehouse on the other side of the planet that have to be shipped through, supply chains that we've found out are quite fragile here recently. So looking to apply additive and other fabrication techniques into more of a mobile fabrication methodology. So we've got some funded work there, and we're trying to stir up some other work, and that'll be fun. It'll be fun to see where that goes. Lots of things on the horizon here for me.
That's awesome. So certainly a lot to keep you busy.
Yes. Yeah. I don't lack for things to do.
Awesome. So last final and kind of final question before we wrap up. So you've shared a few pieces of advice that you share with your students, kind of leverage your network, but anything else? I mean, as someone that may be outside the industry or trying to reskill, upskill, kind of thinking about additive manufacturing and how they can kind of better themselves or kind of get different types of knowledge to be successful in the industry like yourself, kind of what piece of advice might you share?
Oh, that's a tough question. You know, when I teach my introduction to additive course, I make sure to point out, we call it additive manufacturing, not 3D printing, because the 3D printing is just one step in the manufacturing flow. So from the context of additive manufacturing, there's a lot of steps, right? There's formulation, there's CAD, there's finite element analysis, if you're doing that sort of thing. And then there's all these downstream things of how do you finish it? How do you post-process it? How do you do things like that? So I guess my advice would be, don't overlook those other things, right? Because I have students who come to me and say, oh, I bought a 3D, one of the common refrains was, well, everybody's going to own a 3D printer just like everybody owns a personal computer. And my hesitation with that is you still have to be able to create parts. Now, you can go download things for free off of Thingiverse or wherever. But if you're wanting to use this in a creative sense, you still have to have that creative spark, and you have to be able to take that creative spark and turn it into a 3D model that you can represent in an appropriate file and load into a 3D printer. And not only that, but know how to put it on the build plate, how to orient it, how likely it is to fail based on its geometry. All of these things you learn over time. But I would say, the advice for those out there that see this as their career path or want to change career paths is that the pushing the button on the 3D printer is just one piece of it, right? So skills and CAD and skills in simulation, those things are pretty easy to come by, right? I taught myself CAD, a couple of different packages, and you can find YouTube videos to tell you everything you need to know. So filling the void and those skills that are the precursor that everybody tends to jump over and think that you just, take a thumb drive, put it in the machine and press go. There is resources out there to help you with that, all those other things that make it manufacturing, not just 3D printing. And if you can grasp that and you can have skills in that area, now you become valuable to somebody who wants to operate or wants you to operate or come in and help with their operation using 3D printers, because you know the pieces that go into making that successful.
Awesome. Yeah, no, that's certainly great advice. And I think certainly something that folks listening can take with them and apply. So Craig, I appreciate the time today. Excited to see kind of everything you're working on, everything you're building, all the different companies and the work you're doing at Mind. So thanks again for your time.
Yeah, thanks so much for having me.